It is part 2 of section 3.3, feature scaling and stochastic gradient descent method. Let's begin with feature scaling preprocessing. Like other many algorithms, the gradient descent method can be improved in its performance through feature scaling. Here we'll consider a feature scaling method called standardization. For each feature, jth feature, and we try to get mean and variance, and for the feature column, we apply this operation. Then for each feature, now it'll follow the normal distribution of variance 1. Okay. Now, to understand this one, we consider how data is saved. Usually for data, we are using notation X. Okay. That is two-dimensional array. So it is in matrix form, data is saved. And for each row, it is representing a data point. The data points are stacked from top to bottom in this way. So data set is given in this way. And here, for each column, so each column is representing a feature. So jth column, that is a jth column. Now, for column by column, we try to get the mean and standard deviation and try to make such an operation. Then the effect is here. For example, we have such a data, and through this standardization, the center is moved to the origin, so it's a zero mean, and also the variance is now changed to become here unit of variance. People say that the gradient descent method has a tendency to converge faster with the standardized data. However, with the standardization, such geometric feature, geometric characteristics will be broken to become now univariance, so that you have to be really careful. So sometimes maybe the moving here, the center is allowed, or sometimes now just the scaling is desirable, but you have to be careful. And for some cases, it's not really beneficial. Okay, now we go to stochastic gradient descent method. Earlier we learned how to minimize a cost function with negative gradients. The negative gradients are calculated from the whole training set. So such method, gradient descent method, is called batch gradient descent. But now let's imagine we have a very large data set with millions of data points. Then running the gradient descent method can be very expensive because we need to reevaluate the whole training data set each time, so that it's not eventually the whole algorithm may not be desirable when data set is very large. A popular alternative to the gradient descent algorithm is the stochastic gradient descent method. SGD. In SGD, we are updating the weight by using a single data point. Let's see here, mathematical formulation. Given a training set D, XR is feature vector, and YI is its corresponding label, and there are n points. Therefore, I to n, by using 1xi, we try to organize the correction term and update. So it looks like a perceptron, but here in other line we are using identity activation. So the difference will be used for the weight update. Now, after finishing this one, once it is not convergent, then we shuffle D, the data, and now we do again. In real life, data set is saved with, and the first portion is for first class, and next portion is for class 2, and below. Now, some data points are for class 3 and so on, so that when you read the data set from a file, then is recommended to shuffle first. The shuffle first, and now for shuffled data set will be accessed each one in each iteration. So you finish this iteration to finish one epoch. Epoch is used for just the accessing whole data point. Then we finish one epoch. So through an iteration, we finish one epoch right now. So after finishing iteration, now again, and for second epoch, you shuffle in the beginning, shuffle the data set, and again, n iteration. So that is, in reality, it is implemented in most cases. Here, this is properties of stochastic gradient descent method. SGD updates the weight based on a single training example. The method typically reaches convergence much faster because of more frequent weight updates. In the original gradient descent method, whole data is used for one update. Now in SGD, we are updating the weight by using each data point, so that after finishing one epoch, now here the weight can be updated much better. So the convergence can be much faster. And now here, because we are using a single training example, the error surface is smoother. Okay, that means that once you are making such a the sum of least square, sum of squared error objective function, then because of a sum, and sum here, because of it is involving many data points, then if we try to make a picture in 1D, then objective function may have here some local minima, because of many things are involved during the update. Now W is not really correct one during the iteration, so that such objective function can be obtained. Now, so when you are using the original gradient method, you have to deal with this objective function. But when you are using SGD, then because a single the data point is used here at the moment, the objective function is smoother. In fact, for 1, it is coming from one quadratic formula, so that eventually, along with along with one point, it is smooth. So its minimum may not be the same as that one. However, anyway, and it's much better with the gradient descent method. If you start with initial value here, then it is going down and stuck here. But along with SGD, and you can find this minimum easily, even though it is not the same as that one, you can reach it here. And then with other data points, you can move around and you can reach at the global minimum a better way. Okay. Okay. Here now to get here accurate results through SGD, you have to access the data in random order. And if you try to use the access data with a decided order, then possibly the W will be with a cycle, so that here you have to access the data in random order. In SGD, and eta is often said adaptively. So that means that decreasing over the iteration k. So eta k is chosen C1 over k plus C2 with some two constants. That is often happening. Now, also, as one good compromise is mini batch learning. The original gradient descent method is using whole data set for one iteration. Now, in stochastic gradient descent method uses only one single data point per iteration. They are two extreme cases. So rather than these extreme cases, you may try to use a small number of data points per iteration. That is called mini-batch learning. So mini-batch learning can be understood as applying batch gradient descent to smaller subset of the training data. For example, 10 samples at a time or 32 samples at a time. Now, this mini-batch learning is popular in deep learning particularly, and the convergence is really fast, and because now frequent weight updates, but also even though you are using 10, 32 or some other number, however, and modern hardware can be organized so that you can realize the factorized operations, factorization, so that you can do it. Here the computation is done like using one the single data point, even though you're using more than one, but as far as not too large. And for example, the 32 then is almost the same way. The 32 data samples can be used for one iteration, like using only one. Because of factorization, you can do it. If you can save such a time, then Now, why not using a small subset of data set for each iteration? That is the idea of a mini batch learning. So if you are dealing with a huge data, as in deep learning, then mostly you'll use mini batch learning. Okay, that's the end of the section and end of the chapter. Thank you.